The crossover N2 equal to N1, meaning same number of atoms at the second level as in the first level, occurs at about 100,000 Kelvin, as expected from the argument of the exponential. The conclusion then is that very high temperatures are necessary for a significant number of atoms to be in the first excited state. At 10 to the 4 Kelvin, which is about here, less than 1,000th of the atoms are at the N equal to level. And according to the expression that we found for N2 over N1, the line strength should increase with the temperature. Why then the Balmer lines peak at 10,000 Kelvin? You see here the Balmer lines peaking at the A type, and then weakening towards the B and the O. You may already guess what is the reason. That's ionization. At some point, ionization starts to take over because at higher temperatures, the electrons are ionized, then the strength of the line itself is going to decrease. At too low temperatures, few atoms will be at the excited state, but at too high temperatures, also few atoms will be at the excited state because ionization is too high. So we can write Boltzmann levels for the ionization balance. That's what you're seeing here. This is the ionization level, so the number of atoms at the ionized state, N2, over the total number. And indeed, you see here that ionization starts at about 6,000 Kelvin, and at 10,000, you have half of the atoms being ionized. And then at about 15,000, you have all of the atoms ionized. So if you combine both, if you combine the excitation with the ionization, then you'd have a curve like this. The number of atoms in the second excited state of the neutral towards the total number of atoms, both neutral and ionized, you see then that is going to peak at 10,000. So let's see how that plays out. So we can write the Boltzmann levels for the ionization balance. The form is the same as this equation above, it's just that now the states are going to be the ionization states. The ionization potential, that means the energy needed to ionize from the state A to state B, let's call that chi. And then you can also write the degeneracy of the states. Let's call it Ni plus 1 over Ni. These are the ionization states. Then you have that, again, the degeneracy is going to be G plus 1 and Gi. But you also have the degeneracy of the free electron, since now there is an extra particle in here. And then the exponential is the exponential of the ionization potential. So the degeneracy of the ion times the degeneracy of the electron means the number of possible states that the ionization can happen. The Ge, the degeneracy of the free electron, is the number of possible states in which a free electron may be put. Now for hydrogen, Gi plus 1 is simply 1 because there is no electron left. There is only a single state for the proton that lost the electron. And if you assume I to be the ground state of neutral hydrogen, then the statistical weight is equal to 2. Because remember, the statistical weight is 2 times n squared. If n equal 1, that's just equal to 2. So you have then that Gi plus 1 over Gi for the ionization is simply equal to half. So the last missing piece to find for the ionization balance is Ge, the degeneracy of the free electron.